here's our answers. Number one is uniform. If you want to go with a more commonly used word, what does uniform mean?
The same.
They're the same. So uniform or same or matching or anything like that. You can't do a problem where you have kilometers and meters and centimeters like all mixed together in the same problem. You have to have the units all be the same or uniform to be able to do a problem. That was an easier answer that was in blue. Some of these answers were harder to pick up on. Two is dimensional. Dimensional was another one that maybe wasn't so bad to pick up on because it was like dark, bold stuff, dimensional quantities for a fill in the blank. Three was a harder one to find. Right after you had the big bolded dimensional quantities, they explained to you what dimensional quantities meant, but they didn't put that in big blue bold stuff, but that did indeed matter. So the answer for three, a little bit harder to find potentially when you were reading it, but for three, it depends on the system of unit you use. The number depends on the system of unit you use. Like, for example, length is a dimensional quantity. From here to the turnpike, if I said to you, what length is it from here to the turnpike? You might say it's about one. About one what? About 1 mile. But I also might say to you, it's about 1,760. What might I be measuring there? What's 1 mile about the same as 1760 watts? Yards. I could also say to you, it's like 50,000 inches. There's a lot of ways you could measure the distance from here to the turnpike. Depending on the system of measurement you use, you're going to come up with different numbers. We could measure that with kilometers, how many kilometers it is, or whatever. But to be a dimensional quantity means that the number depends on the unit that you use. That's what three was about, but it wasn't easy maybe to see that. For number four, how do you know what kind of unit to use? Does anybody have a strong opinion you had a right answer there? It was a sentence in the book, but they didn't bold or blue it. You use the most convenient one. So if I'm measuring from here to the turnpike, out of 50,000 inches, 1,760 yards, or 1 mile, which is the most convenient one to talk about?
1 mile.
Mile. If I wanted to measure this table, I could measure this table with miles. It's like some tiny fraction of a mile, but that's not probably the most convenient measurement. Or maybe yards, or even inches. None of that would be ridiculous, but miles would be pretty nuts. But there's always a most convenient unit to use. That's the one you want to go with. If we were going to measure how much my car weighed, I don't think we would do that in ounces. We'd go with tons. Like there's a most convenient unit to use. 5 was in here a couple different ways, so depending on which blue sentence you grabbed, I'm probably okay with a variety of answers to some degree here. The basic concept is that the units should match. If you want to say that the units canceled out and match, that's even better. If you want to say the units divide out as factors to give the correct labels in the solution, that's a blue sentence that was in the margin with like a lot of words, but that's the right answer there. But the basic concept here is that the units should match, or even better, that the units cancel out or divide out to be able to match. That's what we're after on 5. If they don't have anything matching on 5, then I'm not sure, but that one blue sentence would be okay. Units divide out as factors to give the correct label in the solution. I would take that. That's a long way to say what I said.
What about it agrees with the dimensional quantities?
Yeah, something about agreement. Anything about agreement and matching, I think I'll take, because that's a harder question to like find and explain and how. Question about top 5 new ones? Then we go flashback to olds. Find my correct paper to do this with. Hold on. So we are a science that examines the relationships of matter and energy. We are total understanding of how the universe works, equations. 9 is D on top, just a D on top, E, B, and C on the bottom. Doesn't matter what order the letters are in on the bottom, but it's all 3 letters on the bottom, E, and B, and C. 10 is scientific notation, 11 is 9.87 times 10 to the 8, 12 is 4.56 times 10 to the negative 4th, 13 is, they have the same powers, 14 is 3.7 times 10 to the 5th, 15 is to add the powers, 16 is 2.1 times 10 to the 10, 17 is subtracting the powers, 18 is 4 times 10 to the 5th, and then we'll cut the video, and I'll can you wait? Next quiz up, we're reading 2.1 to 2.4. And most of this will be new to chemistry this year, although not new to your life. But the reading totality of newness is 12, and I don't recycle much of the old. That stuff will be back on the test someday, but it's going to go away for a bit. So the only 3 questions that live on are, what is physics? A question like 11 or 12 where we're doing some mathy stuff, and a question like 14, 16, 18 where we're doing some mathy stuff. So there will be 2 mathy questions, 1 from each of those little mathy groups. What is physics? And the other 12 are newbies. Let's run through the notes paper that I gave you just to explain what this is, and that'll explain how to do the newer homework. So there's a lot of different things this year that we'll be keeping track of in terms of measurable quantities from the real world. First of which, on this paper, I put mass on there. It's going to be important for you to know 2 things. One is that mass, when they do their equations, is always going to be the variable m. So when you see the variable m in an equation, that's mass. However, sometimes you also see an m for a unit on things. If you see a unit of m, that's actually measuring a thing called distance or displacement, because this m on line 2 stands for, what's this m? The second line.
Meters.
Meters is correct. So if you're reading a paragraph, blah, 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 10m, this m stands for meters. But if I write an equation on the board, like F equals ma, this m stands for mass. Okay, so we have to understand the difference between the variables and what they represent versus when you have measurable amounts, there's abbreviations for those measurements. Okay, so mass in an equation is an m. The unit for mass is kg, standing for kilograms. If I'm talking about distance or displacements or lengths, things like that, the variable for some reason for that is an s. You would think d for distance, but sorry, that's not how physics got invented by whomever. They decided to do that as an s, not a d for distance. The standard unit we're going to most often use for distance measuring is meters. Time. The variable for time is a t. The unit for time is s meaning seconds. Seconds is going to be most often what we measure time with in here. Speed, semi-synonym for velocity. The variable for equations is going to be a v. Over here I see some v's. V for velocities over there. The unit for that is meters per second. Density, you'll never have a density equation, so it doesn't matter what variable that they want to do for density. The standard unit is on that page, it's kilograms per meters cubed, but that's not a huge deal. Acceleration is an A, that's meters per second squared. Area is a big A, that's square meters. Volume is a big V, that's cube meters. We'll come back to this paper in a second, but let's use it first to do a sample problem or 2. In the homework, what they're going to do is give you an equation and ask you if it's dimensionally correct. So if I say V equals AT, maybe that's dimensionally correct, maybe it is not. You need to know that V stands for velocity. Know or look up the unit for velocity on the paper I just gave you, which is m over s, like meters divided by seconds. Then we need to look at acceleration. A stands for acceleration. Grab the unit for acceleration, which is m over an s squared. What are those letters doing to each other?
Multiplying.
Multiplying. T stands for time. Time is measured with seconds. And if you want to make this a little more fraction friendly, you could write it on top of a 1. Did any of those units cancel at all? Yeah. One of those seconds can cancel one of those 2 seconds. And if we cancel them, do those units agree with each other? Yes. So that equation, yes, is dimensionally correct. Let me try again. V again stands for velocity, measured with m over s. S stands for distance, measured with meters. T stands for time, measured with seconds. Are these 2 sides of the equal sign doing the same thing? No. They might have the same letters, but over here they're multiplying, over here they're dividing. So no, that equation is not dimensionally correct. So to flash back to quiz answer 4, I think it was quiz answer 4, no, quiz answer 5. To know if an equation is dimensionally correct, the units have to cancel out and end up matching each other, which these did, those did not. Question about that concept? So here's what the homework is about. On the new homework, we are going to do number 41. 41 has ABC. There's 3 equations like these, where you're going to use a little guide I gave you of which units stand for which things, and just see if they cancel out to match each other and say yes or no. Then at the end of each chapter, there's an assignment called the chapter review. So we're going to look to go do the chapter review. In the chapter review, there's questions, and the syllabus will tell you to do questions number 1 and 2. The questions are usually pretty easy, and this chapter is not an exception. The questions are coming straight off the quizzes that we've been doing. There's no big surprises in the questions. The problems are usually medium to hard, but not in this chapter. We skipped around this chapter, if you remember. So the only problem we're going to do is problem number 5. 5 has A, B, C, D. It's 4 more questions like these, where you try to put the units into the problem and just see if there's agreement with the units when you're done. So 5, A, B, C, D, doing that again. And then there's a third group where sometimes we'll do some of it, sometimes we don't do any of it. It depends on the chapter. There's a group called Applying Physics. We're going to try the Applying Physics number 1. And this is what I ask is everybody on those at least try to do anything. But some of you are not going to have real frequent success maybe on those. If you're planning a future in like the engineering world of life, you want to take those questions more seriously than the people that are not in this room thinking about an engineering future. If you're planning an engineering future, these applying physics questions are the kind of things that you're going to have to figure out in your career. So if that's what you're thinking you might want to do, take the applying physics a little more seriously than the rest. But for everybody, just try them. Just give it a try. See if you can figure it out. And that's the homework for tomorrow is 41, 2 questions, 1 problem, 1 applying physics. At least try it. Do something with it. We have 1 more little tidbit to fill in on this sheet, but question about those concepts. Just to give you some idea of what's what, I have on the bottom of this sheet a little bit of a mini conversion, kind of helpful fact. Our book will be all metric all the time. And young American students sometimes have trouble getting their minds around sometimes what those numbers mean. Does anybody have any idea about how much a kilogram is in the more familiar pounds world? Anybody have a clue about kilograms, pounds, what's up?
2.
Yeah, that's pretty good. 2.2, even better. But a kilogram is about 2.2 pounds. So if you're reading and something weighs 100 kilograms, it's like about 220 pounds. And maybe having that written down somewhere might help you once in a while get your mind wrapped around what's going on. Anybody have any clue, kilometer per hour, what that has to do with miles per hour ballpark? If you have a car that still doesn't have a digital readout, but it actually has like the gauge that goes up or down, is the kilometer per hour speeds, are those like way higher or are those way lower than your mile per hour? Difference of opinions. They're way higher. 1 kilometer per hour is about 0.6 miles per hour. So if you're going about 60 miles per hour, you're going like 100 kilometers per hour. The kilometer scale of numbers is a way higher set of numbers than your mile per hour thing. If you're going like, yeah, that's enough on that. Meter per second is about 2.2 again. So if you're 1 meter per second, you're about 2.2 miles per hour, give or take. So those three are there just to give you some idea when they are telling you stories, just to wrap your mind a little bit better around what it is. These bottom two you actually need. Uh-oh.
Why is your ringtone that sound?
I'll grab that from you in a second. The second one from the bottom, just fill in 5/18 for now. We'll use that some other day. And the very, 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 very bottom one will be 18/5. You don't have to memorize those yet, but those will come into play some other day. And you can cut that off.